and is the acronym for State of Texas Advanced Resource Recovery Program. So it has been around for around, I think, close to 15, 16 years. It's funded by the state of Texas. And I recently updated the mission when I arrived in 2021. And the mission essentially is to conduct geoscience and engineering research to increase production and profitability of earth resources, including oil, natural gas, hydrogen, geothermal, and minerals. When I introduce our mission, I keep saying, you know, our bread and butter is oil and gas. And I foresee that this is going to be the case for a few years. So we cover a wide variety of topics that go from water resources, mineral and air resources, energy, land resources, geohazards, and special projects. For the energy group, we're around 11 full-time researchers. We have postdocs, students, and so on, but STAR funds more activity within the Bureau. So today I'm going to be talking about hydrogen and hydrogen storage in salt bodies, and this falls mostly into the special project box, okay? So I thought it would be a good idea, you know, when we talk about the energy transition, oftentimes we forget the word transition. It will take time, and as that happens, we are also engaging in this learning process. What is hydrogen, and why are we talking about hydrogen, and why do we need to store hydrogen? So I thought it would be a good idea to give a little bit of an introduction. Hydrogen offers options for a possibility to lower our emissions or carbon emissions. We can do that using fossil fuels and generating hydrogen as we do today, but including CCS. We can also do that with green hydrogen from, you know, renewables. We'll talk about that in a bit. It is transportable. You can use pipelines, but it's not that straightforward. You cannot just put 100% hydrogen on a pipeline. It's not going to work that way. It can be liquefied. You can do ammonia, but then how do you transport the ammonia? You maybe don't want to be trucking ammonia, you know, from one place to another. It is storable, but we need large-scale storage, and I'll talk about that in a second. And again, multiple sources, multiple ways to do this. So essentially, this is from DOE. I like it because it shows kind of the ecosystem. Oftentimes, people think about hydrogen and cars in California. The game changer with hydrogen is really to use hydrogen for hard-to-abate industries, cement, steel, shipping, also in terms of transportation. It's not only fuel cells, you know, it's the big items where hydrogen can actually play an important role. Hydrogen in the news, we'll hear about this all the time. I think it's worth visiting the DOE webpage on the hydrogen shot, where essentially they put the ambition in one sentence to cut the cost of clean hydrogen to $1 per kilogram of hydrogen in 1 decade. So that's equivalent to reducing cost of production by 80%, which is a lot. And then the other thing that is important is what does clean hydrogen mean? And essentially is produced with a carbon intensity that is equal or less to 2 kilograms of CO2 per kilogram of hydrogen produced. Okay, so that's important to keep in mind. There are many projects in different places. I update this slide each time I give this talk, but it's not hard to find, you know, news items where they talk about hydrogen. I think something was mentioned today also earlier. You know, I'm a geologist. I'm not an engineer. I need pictures in my head. So 1 kilogram of hydrogen is more or less equivalent to 1 gallon of gasoline, which is more or less equivalent to 33 kilowatt hours. The thing that is important with hydrogen as a gas is that hydrogen has 1/3 energy as natural gas by unit volume, meaning I need 3 units of hydrogen in gaseous form to generate the same energy that I generate with 1 unit of methane. This is in gas form, right? So you're going to start to think about what that does in terms of storage. Hydrogen production, the United States right now is producing more or less 10 megatons of hydrogen. Most of it, 99% of it, is derived from fossil fuels via steam methane reforming of methane. Global production is around 70 megatons. And again, 98% from fossil fuels, but around 25%, 20% comes from coal gasification, mainly in China. So you probably have heard, all these colors with hydrogen. It gets very confusing sometimes. But essentially, when we're talking about black hydrogen, we're talking about coal gasification without CCS. And the number that I think is important to get is 1 kilogram of hydrogen is produced, and the CO2 emission is around 20 kilograms of CO2. Remember that 2 kilogram CO2 target for the definition of clean hydrogen. Then we have gray hydrogen, which is how we produce most of our hydrogen in the US. And that goes down to around 8.5 kilograms of CO2 per kilogram of hydrogen. In terms of cost, these two are the cheapest ones, with production cost around $1.3 to $2.3 per kilogram of hydrogen. On the other end of the spectrum, we have green hydrogen that is essentially using or harnessing renewable energy, either solar or wind, to feed electrolyzers to break the water molecule and produce hydrogen. It sounds great, but for each kilogram of hydrogen produced, you need around 9 kilograms of water, and it has to be relatively clean. So it's a big challenge, and the cost, as you can see there, is not cheap. Then you can also use nuclear, and so there are a bunch of colors. I try to keep in mind is the hydrogen shot definition. What is clean hydrogen and how we produce that. Comparative hydrogen production cost, according to DOE, you will see differences with the previous slide. It depends on where you look. But you can see here the different options that we have today, from coal gasification without CCS to solar electrolysis, and how the cost can go from more than $1 to around $8. Remember that we want to stay here in the $1 per kilogram by 2031. So when I see the dates, oftentimes I say, good luck. It's a huge challenge, but it's a good one. And I have to emphasize, I think in this transition, hydrogen will play an important role. It's the thing that I think can get us there. It's not going to be only CCS, some of the talks have hinted. In terms of projected US hydrogen demand, the demand, again, by 2050, if we increase that demand by 10%, we're talking about the equivalent of 14 TCF of hydrogen, which is equivalent to more or less 30 million metric tons of hydrogen. The other commenting here, and this is a talk by itself, if you don't have a market, then there is no point in making hydrogen. So, thinking about how the demand is going to work, it's extremely important. But shifting gears a little bit into the storage component, let's say that today we want to replace 10% of natural gas in the US with hydrogen. Let's make that exercise in our heads. If we want to replace that 10% of natural gas with hydrogen today, we will need around 1,000 BCF of additional hydrogen storage capacity to make it happen. Right now in the US, we have between 5 to 8 BCF of hydrogen storage capacity for purposes that are different to energy production. So it's humbling, which makes me feel confident that we're going to have a job in 10 years. So then, why hydrogen storage and why big? Hopefully I'll be able to give you a little bit of a scale here. I really like this plot. It shows on the x-axis power from kilowatts to gigawatts. And then in the y-axis, it shows discharge time from seconds to days, right? So hydrogen, for what we want it, or what the conversation is about, will need to be something that we can also use seasonal, you know. And for that to work, we will need, what we're talking about is bulk power management, right? It's something that will allow us to store, deliver gigawatt scale, you know, stuff for periods of times that go from days, weeks, even months. So we're not talking about your average battery here. You know, batteries have a place as well, you know, in the system. But for what we're talking about, at the scale that we're talking about, we need that kind of storage, huge, you know, and only subsurface storage can provide that. Again, just to compare things, this is the Vistra Energy's lithium-ion battery system in Moss Landing. This is the largest one in the world. And this is just one of the phases. I think it's larger now and with more capacity, but one of the phases has around 4 hours storage duration, you know. When you think about that facility and this phase, we're talking about, it is connected to the power grid today, so nothing renewable about that. It spans the length of 3 football fields. It's quite big. We're talking about around 4,500 stacked battery racks, each containing 22 individual battery modules. So think about lithium, cobalt, nickel, I mean, all the minerals that are in that to produce that. And we're talking about something close to 500,000 feet of wires and cables that is equivalent to the distance between Philadelphia and New York. Again, these facilities have a place and we need them, you know. But if we're talking about seasonal storage, then we're talking about gigawatt hour capacity. And for that, we need the subsurface. And we're not strangers to this. We store natural gas, we store liquid hydrocarbons. I mean, everybody has heard about the Strategic Petroleum Reserve. We can do this. And there are several ways in we can do this. We can do this with porous media, either aquifers or depleted reservoirs. And we can do this using salt formations. What I'm going to be talking about today is salt formations, okay? Because storing hydrogen on porous media is a whole lot more complicated for other reasons. So I'm going to concentrate on salt, but I want you to keep in mind that porous media is also an active line of research and an option. So once again, coming back to this idea of like 10% natural, 10% replacement of natural gas by hydrogen, needing 1,000 BCF of additional storage capacity. This exercise here was actually made by Simone et al. We're not endorsing this, but essentially what they did was they look at the salt domes along the coast, Gulf Coast of the United States, took some approximations in terms of size, depths, you know, how many caverns you can put in each of these salt domes, and based on that, you know, if you run a rough estimate, you can have around 2,500 to 3,500 BCF of additional, you know, hydrogen storage capacity on those domes. So it's not trivial. It's good. If you're like me, even though I'm a geologist, I really didn't know this whole thing about salt caverns. What are these salt caverns? I mean, what's the deal here? You know, this thing, and essentially it's not new. You know, it has been around since the early 1900s. And essentially, what you do is you drill a well and you inject water. By the way, if you want to dissolve 1 unit of salt, again, this 1 to 9 thing comes in, you need around 9 units of water. And it has to be relatively clean because you're essentially dissolving salt. And then you're also producing the brine. So you need to do something with the brine, going back to this water management situation. But anyways, so these salt caverns have been used for a wide range of things, from waste disposal, from oil and gas operations, and oil and gas storage, salt mining by solution mining to produce the salts and things like that. And there are thousands, this is the first thing that was shocking to me, there are thousands of salt caverns around the United States. I was just totally ignorant on this. I didn't know that. Probably the most famous user of these salt caverns is the Strategic Petroleum Reserve. They have 4 localities along the Gulf Coast where they actually store liquid hydrocarbons. So each salt dome can have up to 60, 70, 80 caverns each, you know. And this is how the seismic looks like with the salt domes in there. One of the challenges is that onshore seismic is not that great, so it's difficult to see inside. But let's see. The other thing is, in terms of the size of the caverns, each cavern can be around 200 feet in diameter and up to 2,500 feet high. But this is the case with salt domes. Embedded salts, these caverns are a whole lot smaller, okay? There is hydrogen storage in salt formations today, okay? There are 4 locations around the world where we're storing hydrogen today. 3 of them along the Texas Gulf Coast in salt domes, and 1 in Teesside in the United Kingdom, embedded salt. So you can see here some of the numbers. This is the amount of hydrogen in tons for each of these locations. This is the one in Teesside in embedded salt. You can see that it's smaller, and this one is in a Spindletop, which is the largest one. One of the limitations with salt domes is that these salt domes are geographically restricted to certain areas. So in the case of the United States, you know, on the Gulf Coast and maybe here in Utah, you know, but bedded salts are broadly, you know, distributed. The concern with bedded salt is that they are more heterogeneous, okay? So it's more complicated to plan around that, but that's fine. And then porous media would be more spread out, but then it's more complex because hydrogen is smaller, it's really reactive, and it brings a lot of other issues. But even for salt domes, what we're learning on this is that salt domes are not homogeneous and nice and just halite, you know. What we're learning, especially from looking at the operational experience from the Solution Mining Research Institute, is that these salt domes can be very heterogeneous internally. I'm trying to see if much time I have. Yeah. So it's not as simple. And, you know, these 3 locations along the Gulf Coast that are storing hydrogen is mainly strategic in purpose, because this hydrogen is used to remove sulfur from hydrocarbons and for the petrochemical industry. And essentially, you don't want to shut down your refinery because that's very expensive. So if your hydrogen supply gets compromised, then you get untap the hydrogen storage thing. But for what we're talking about in here, we're talking about high-frequency injection withdrawal cycles for power generation. And then we're talking about, you know, injecting and producing hydrogen, you know, and in several times in a month or several times in a week. So how is that going to look like from an operational perspective, you know? Some interesting stuff, you know, this is a Big Hill dome in Jefferson County, Texas. And actually, this is the site of one of the SPR locations. And things that can happen, you're drilling, you're leaching your cavern, and in this particular case, one of the caverns encountered 150 barrels of hydrocarbons. Other caverns find methane as they're leaching or stuff like that. The problem with that is, well, there is a safety concern, of course, but also there is an issue with contamination of your product. So in the case of hydrogen, what do you want your hydrogen for? For power generation, for a cement plant, or for fuel cells? If it is fuel cells, it needs to be 99% pure. Therefore, you cannot contaminate your hydrogen, you know? And then there are issues with leakage and things like that. This one is Barber's Hill. This is sonar. You know, by the way, building one of these caverns can take between 2 to 3 years if you know what you're doing. So if we need to build hundreds, how much time is that going to take? maybe repurposing should be an option. But in Barber Zero, what you see is that as you leach, these caverns are supposed to be cylindrical and uniform if you only have halite. But what you see here in the sonar image is that after you hit certain depth, the cavern starts to widen. And you start to develop this kind of plane that is coming through you. So why is that? So it can be a combination of things. It can be that the minerals are changing. So instead of halite, you maybe have more anhydrite. So what's going to happen if you put hydrogen in contact with anhydrite? Then you have H2S. Not good, right? So is this a shear zone? It can be that you have a shear zone also in the soil. So these are questions that we have that need some answers. I'm not saying that this is not doable. The solution mining industry have been doing this for decades. These guys know how to do these things. What I'm saying is that the upscaling for hydrogen storage is going to take more work. And I'm also saying that the requirements, the field development requirements, the safety requirements of big corporations that probably will invest billions of dollars on this have a lower tolerance to the kind of things that happen in terms of operations in here. And my last assignment in industry was in field development in Norway. I read these reports and sometimes I'm like, what? So there's no way that's going to pass. So I think I'm going to skip some of this. Green hydrogen, why is this important? This tornado plot is showing you curtailment of wind power in the United Kingdom. And in 2020, that was around 3.7 terawatt hours. So, oftentimes we say, well, the wind is not always blowing and the sun is not always shining, but sometimes it does. And it generates extra capacity that the system cannot absorb. So the idea with green hydrogen is to harness that and use it for the electrolyzers, get your hydrogen, and then store it, and then use it when you need it. So this curtailment here, this 3.7 terawatt hours, cost the UK around 274 million English pounds in 2020. And you see the projections for 2030. So that's the thing with the green hydrogen. I think I'm going to finish. Well, I have 2 slides. This one, Texas, I need to talk to Texas, of course. And it's showing you essentially what we're trying to do is to see where are the resources and the collocation of above and below surface resources. That's important. If you don't have the right infrastructure in place, if you're not closer to the market, doesn't matter what you have in the subsurface. There's no business case, okay? So essentially in red, you can see salt domes. The background is hydrogen potential from wind. So you have this is Corpus Christi around here. Then you have these hydrogen pipelines. This one here is a salt cavern that is here in one of these domes. And then these are the wind farms, right? And what you're starting to see is companies starting to highlight areas where they think they can make a business case to develop this thing. So we'll see how this evolves. This is the same for sun, same concept. Some studies in the Permian Basin, this might be, relevant to you guys here in Oklahoma. This is New Mexico. And we're also starting to see how these bedded salts look like in the Permian Basin. More challenges because they're more heterogeneous. The more heterogeneous it is, the more challenge in terms of reactions with hydrogen and so on. So I have a postdoc working on this. This gives you an idea of these variations. We are actually writing this code to try to understand the thermodynamics of hydrogen on these salt caverns and how these pressure temperature variations work in time to try to imagine how that's going to look like. And this is my final slide in here at BEG in the 80s, late 70s, early 80s, people were talking about nuclear waste. And there was this huge DOE program. Those of you who have heard of Martin Jackson, for instance, he was one of the ones who led this. And they collected a lot of core. And I have been digging into some of this core. And sure enough, I mean, this is coming from salt domes. Not all salt domes look the same, You have this pristine, nice halite. This is how I imagine salt domes were before I got here. It's like, it's all nice and pristine. and then you have some impurities in there, and then you have some crystallization in there, and then in the cap rock you have some anhydrite and stuff like that. So it's gonna take some time. I think it's fascinating. I think it's doable. We're gonna do this, but I think it will take some time. So with that,